Hi everybody, John Accardo here. Welcome to part 2 of this series covering the FS200 clamp-on utility software. In part 1 of this series, we covered accessing and downloading the utility to your PC. Now we'll begin to drill down into the application and look at the various features and functions that it can offer you in working with your clamp-on ultrasonic flow meter. In this session, we'll talk specifically about sizing for gas applications. To get started entering your application information, all you need is for the FS200 utility to be open. There's no special setup required and no connection to your flow meter is necessary. Just simply go to the Utilities tab, click it, come down to the Clamp-on Gas tool, click it. This will open the gas sensor sizing tool window where you can begin to enter your application information. When you open the window, any data that's currently populated in the entry boxes is data that was entered during the previous usage of the tool. When you close the window, all the data that you entered is retained, so the next time you reopen the window, it remains present. Before you begin entering data, you might want to go across the top of the screen to check all the default settings for entry values. You'll notice a number of different entry parameters for length, temperature, pressure, and so on, with a default associated with each one, which you can configure to match your particular application requirements. Beginning on the left side with length, you can enter your dimensions in inches or millimeters. Obviously, temperature in degrees Fahrenheit or degrees C. You have a number of different units with which to enter pressure. Currently it's set to PSIG, but you can also use PSIA, and of course bar and kilograms per cubic meter and so on and so on. Velocity entries can be in feet per second or meters per second, and this applies to both speed of sound and flow velocity. Density has an associated group of values, including specific gravity, pounds per cubic feet, kilograms per cubic meter, etc. And then you can also enter your flow rate units. You can choose both a volume unit and a time unit, so that you can enter things like cubic feet per hour, cubic meters per second, cubic meters per hour, and so on and so on. To begin creating our application, the first thing we want to do is enter our pipe dimensions. Also, because gas applications require the use of high-precision flow sensors, the applications that we measure are generally confined to steel pipes for which the high-precision transducers are designed, and also plastic pipes, which enable the use of high-precision transducers as well. Because of this, the pipe material default is steel. However, you can also hit the drop down, and even though many other pipe materials are listed, the only other ones that are suitable for gas measurement are plastic pipes. Obviously, the last time this tool was used, it was programmed for an 8-inch Schedule 40 pipe because you can see the dimensions are still there. So let's enter something new. Let's work on a 12-inch application. So we'll highlight the pipe outside diameter and enter 12.75, the OD of a 12-inch ASA carbon steel pipe. Unlike the flow meter, which has built-in pipe tables, to utilize the FS200 tool, you'll need to know your actual pipe dimensions. These dimensions are readily available online. You can look up pipe schedules and wall thicknesses for various dimension pipes, or you can always contact Siemens Technical Support for information about pipe dimensions. With our pipe OD entered, we can now enter our wall thickness, and our application pipe is a 12-inch standard wall pipe, and standard pipe wall is 0.375 inches, so we'll enter that. In the unlikely event that your pipe has an internal liner, you can enter the liner material by clicking the drop-down box and selecting the material of the liner, and then if you do so, you would also enter a liner thickness. Since our pipe doesn't have a liner, the liner thickness entry is just grayed out. Now with our pipe dimensions entered, we can continue on to our gas itself. As you can see, the previous selection was natural gas, And based on the information here of temperature and pressure, the estimated sonic velocity of that gas is 1372 feet per second. Beyond natural gas, there's also entries for single component gases or noble gases, and you could also enter your own gas composition if desired by coming down to the Use AGA8 gases selection. Here you can enter the mole fractions for your specific gas if it differs from a typical natural gas. We'll talk more about using the AGA8 gas entry for your specific gas composition a little bit later in the program. For now, we'll just stick with natural gas. In addition to the gas selection, should you have more precise information about the sonic velocity of your specific gas, you can enter it directly in the estimated VS box. You can also enter viscosity if necessary. Beyond the gas selection, you can also enter the application parameters, such as your flow rate, your temperature, and your pressures, both at minimum conditions and maximum conditions. When you look at your flow rate, you'll notice to the right there's a multiplier attached to the actual flow rate itself. So in this case, it says 1 minimum and 1 maximum in millions of standard cubic feet per hour, because we're selecting standard cubic feet as our volume unit and hours as our time base. When you enter a value for your flow rate, the tool will automatically apply a multiplier. So for example, if our minimum flow rate was, say, 500,000 standard cubic feet per hour, we would have to enter 0.5 million, because right now we're in units of millions. Once we do that, notice that the multiplier changed. It now changed itself to thousands of standard cubic feet per hour. So our flow range now is 500,000 to 1 million, or 1,000,000, which is a million. If we were to change that back to 1,000,000, it would change back to a million as the multiplier units. Our temperature can be entered. Let's say our minimum temperature is going to be 50 degrees Fahrenheit and our maximum temperature will be 80 degrees Fahrenheit. And then we come to pressure. In our application, our min pressure will be 400 psi and our max pressure will be 800 psi. Pressure is an important value for your application information because every application has a minimum pressure requirement, and that's a function of the pipe dimensions and the flow sensor selection. This tool will actually identify for you what the minimum recommended pressure is in order to ensure that you get proper conductivity of the sonic beam through the gas. The pressure causes the gas to become more dense, which enables the sonic beam to conduct through it more easily. Once we've entered all our application data, we can come down to the Calculate button and click Calculate to get feedback on our application conditions and our installation information, and also the identification of the proper flow sensor and the mounting method for those flow sensors onto your pipe. If we look across the center line of the tool, we'll be able to see what flow sensor is recommended. And as I mentioned earlier, the high precision is the flow sensor that's recommended. This is not only because we're working with a steel pipe, but because it's a gas application. And gas applications require the use of high precision sensors because they create a Lamb wave which is necessary to perform clamp-on ultrasonic measurement of gas mediums. Besides the selection of the sensor type, the sensor size that's recommended for this application is a D1H, and this is specifically tied to the wall thickness of the pipe. The D1H flow sensor is the one that best resonates this pipe and therefore is the only selection that's suitable for this pipe. If we click the drop down, you'll notice that's the only one with a star next to it, and everything else is in just alphanumeric order. The tool will also give you the recommended part number of the flow sensor so you can match that up to your sensors to make sure that they are the same. And then it goes on to give you the mounting method. Now this mounting method is how it's recommending you put the flow sensors on the pipe. Reflect for traverse is a condition where the sonic beam will actually cross the pipe, reflecting off the far wall back and again, so you actually cross the pipe 4 times. This is a function of the size of the pipe, the selection of the flow sensor, and the flow velocity itself, based upon your entry of flow rate. If the flow rate is higher, the tool may provide a different mounting method. This is all a function of the amount of phase shift imparted by the flow velocity. And the tool utilizes an algorithm to determine the best mounting mode so that your flow velocity doesn't exceed the capability of the flow meter. If we come down to the lower portion of the screen now and click on the installation calcs, you'll notice that the spacing recommendation is nominal 26. So a nominal is the spacing offset that's recommended, and 26 is the number index. So that would be the position on the spacer bar where you would locate your flow sensors. The tool also provides what's called the LTN, which is actually the physical dimension between the flow sensors when they're on the pipe. So in this case, 7.5 inches is how much space there would be between the 2 flow sensors when they're installed properly on your pipe at this number index. And you'll see that there's a minimum operating pressure requirement. This is 174 psi. So what the tool is telling you is that this application, based upon the dimensions of the pipe and the flow sensor, requires at least 174 psi for proper flow measurement. It goes on to give you flow velocity limits. With the flow sensors mounted at the reflect for traverse position, you can see a maximum of 47 feet per second in your application. If your flow velocity is going to go higher than that, it's better to choose reflect, which is to traverse in the flow meter. So if we choose reflect to traverse, for example, notice that now you can go to 94 feet per second because there's less phase shift occurring on the upstream versus downstream receive signals because of the flow velocity. So let's just give you an example of that. Let's go back to the recommended mounting method, and let's raise the flow velocity some. If, let's say, our maximum flow velocity is 10 million standard cubic feet per hour, and we now hit enter, notice that the recommended mounting has changed now to reflect. And that's because our flow velocity, if we go to the gas process calcs, is now 59 feet per second at the high end. And of course, this is a function, since we're working in standard cubic feet, this is a function of temperature and pressure. So when we take 10 million at 80 degrees Fahrenheit and 800 psig, that computes to be 59 feet per second. That exceeds the limit for reflect for traverse, so the tool has now changed its recommendation to reflect mounting so that your velocity does not exceed the capabilities of the flow meter. Should your velocity go significantly higher, in this case we know that the maximum velocity we can see is 94 feet per second in this mounting mode. If you had an application that could flow higher than that, then the tool would have recommended direct mount, which is only one traverse, so has the minimum amount of flow impact on the sonic beam. If you notice, even though we're in reflect mount, the minimum operating pressure has not changed. That is not affected by the mounting mode. It is simply a minimum requirement to ensure that your sonic beam will conduct through the gas. You can also see the range of sonic velocity that's acceptable. It's very unlikely that you'll see a gas that's going to have a lower speed of sound or a higher speed of sound than this range that the meter is providing. If we look at the gas process calcs, you can see some additional information about your application, such as what the compressibility factor is calculated to be, the specific gravity of your gas at the minimum and maximum conditions, the speed of sound of your gas at the min-max conditions, and of course the flow velocities we've already seen, and your Reynolds numbers. So as you can see, the Reynolds numbers are well up into the turbulent flow range because of the low viscosity of gas. So right now, everything about this application looks great. There's nothing showing that there's any kind of concern for the application conditions. But suppose we had an application where down at the low end, maybe our pressure was kind of low. It was only 100 psi. So we can enter that. And now when I hit enter, notice that we get an indication of an application problem in red down at the bottom of the screen. And a new tab has appeared for application problems. And this gives you the details about what that problem is. So let's click on that and notice that it says pressure may be too low for clamp on. And again, this boils down to the fact that the minimum pressure requirement is 170 psi. So since our low pressure is below that level, we're getting an application problem. If we ensure that the pressure is sufficient, go back to the 400, that goes away. So the tool will in fact point out if an application condition is outside the limits of recommendation for operation of the flow meter. So what if our application pipe size was different than what we entered? Suppose this is a 12-inch pipe, but it's a bit heavier wall because of high pressure. Suppose we had a 640 wall. We'll put in 0.640 and hit enter. And now the tool will recalculate the recommended flow sensor. And notice that the high precision sensor is still selected, of course, but now our recommended flow sensor is a D4H. And that's because of the thicker pipe wall. Also, if you notice, the recommended pressure has gone up. So the minimum recommended pressure now is 295 psi, and that's because of the dimensions of the pipe relative to the flow sensor that's selected. And you might think, well, that's kind of high pressure, but that's because of the thickness of the wall. And why would you have a thick wall except to have high pressure? So generally, it stands to reason that you need a higher minimum pressure, and that's because of the thicker wall, which is there because of the higher pressure requirement. Now, I said earlier that we always use high precision flow sensors for gas applications, and that's true. However, there is one point at which we deviate from this requirement, and that's if the pipe wall is greater than 1.25 inches. Once you get above 1.25 inches, there is no longer a high precision sensor that's suitable to match that thickness. So what do we do then? So if we enter a wall thickness of 1.5 inches, that's a very, very heavy wall. Now if I hit calculate, notice that it says down in the middle, can't make a recommendation. It still sticks with high precision, and now it's showing a B1, which is a very small flow sensor and would not be suitable for this size of a pipe. Notice the application problem has come up again, and if we click that, we get all sorts of application problems. The flow velocity exceeds the limit of the installation. That's because of the small flow sensor. Poor sensor match to pipe wall. Poor diameter to wall thickness ratio, because it's a very thick wall relative to the diameter. It's less than 10:1 ratio. You'll get that alarm. Excessive wall thickness. Excessive wall thickness for a high precision sensor. And finally, pressure may be too low for clamp on. Why would that be? Well, now we see that the pressure requirement is 500 psi. And remember, our min pressure is 400. So all of those application problems pop up. So what can we do about an application like this? Well, this is the one and only time where a universal sensor is recommended. The only universal sensor that's suitable for gas flow measurement, and only when wall thicknesses are greater than 1.25 inches, is the E3. So if you notice, if I click the universal selection, the E3 came up. And if I click the the selection box, you'll notice that that is the only universal that's available for selection. So now if I look at my application problems, the only ones I see is flow velocity exceeds the limit of installation and the pressure may be too low for clamp on. So if I raise the pressure now, let's go from 1,000 at the minimum end to, let's say, 1,500 psi. Now hit calculate. Again, it's going to select, we'll have to go back and select universal, E3. And now the only application problem we have now is that the flow velocity exceeds the limit of the installation. And there's a very good reason for this. If we look at the installation calcs, we'll see that we are at 2.3 cycles of delta T. That means that the downstream signal and the upstream signal are separated by more than 2 cycles, which is perfectly acceptable for a high precision flow sensor, but not so for a universal. When you're using a universal flow sensor, it's recommended that the upstream versus downstream phase shift never exceeds 1 cycle. So if I was to drop my flow rate here back to, let's say, 1,000,000, you'll notice that the cycles of delta T are only 0.23 now at the high end and 0.35 at the low end, and that's because of the pressure differentials. One thing you'll notice here is that when I hit enter, the tool recalculated the application information and of course reverted back to the selection of high precision flow sensors. This is something that the tool does. Anytime you hit enter, it causes the calculations to be repeated and it reverts back to its default algorithms. So we'll once again have to tell it that we're using universal flow sensors. And now you can see that the alarms have gone away and we have an acceptable application once again. So now let's revert back to some normal size pipe again. Let's put the wall thickness back at a standard wall. And everything is happy again. We have our standard pipe size, steel pipe, D1H sensor recommended. Everything is good. Now let's change our pipe material to plastic. So we'll say that we're working with Kynar, which is probably the most common plastic we see in gas applications. Hit calculate, and now notice that we've got a slightly different selection of flow sensor because again, this has to do with the resonance of the pipe. But the thing that I want to point out here is if you look at the minimum operating pressure, it's gone to 0. That's not a flaw in the system. With plastic pipe, there is no pressure minimum, and that has to do with the density of the plastic versus the density of the gas. Because the plastic is much closer to the density of the gas, we can operate at much lower pressures. And in fact, we have operated on gas applications at partial vacuums when contained within plastic pipes, which makes the gas meter suitable for things like flare gas applications where pressure is extremely low. So again, these are little aspects of an application that you can test with this tool. You can put in different values and see what the results are. You can be notified if an application condition is not acceptable and the reasons why. So you can certainly always feel free to play around with the tool and try different settings. You won't break anything. You won't get into trouble, but you'll certainly get valuable feedback. So now let's look at the gas itself. We've been working with natural gas up to now. Let's go back and change ourselves back to steel pipe. Hit the calculate, so let's revert everything back to the way it was. When you choose some other type of gas, let's say we choose nitrogen, you'll notice that the speed of sound is recalculated automatically for that gas. Suppose we do have a natural gas, but we have some sort of unique gas composition. We can use the Use AGA8 table now to enter that gas composition and get better information about the expected speed of sound as well as the spacing information, and better ideas of the compressibility factors and so forth. So if I click the Use AGA8 tab, that opens up this button down at the bottom of the screen that says AGA8 gas composition. You'll also notice that the estimated speed of sound has gone to 1312, and that's because there's no value entered for the AGA8 gas, so it just simply reverts to that value. But we'll see what happens once we enter our composition. So when we click this button, it opens up the gas composition and mole fraction percent window, which will allow us to enter the actual composition of our gas. So we can begin entering the mole fractions, beginning with methane, and then I'll just speed the tape up a little bit so you don't have to sit around while I enter all these values manually. Once you've entered all your gas mole fractions, just click the Normalize button. This will bring your total to 100%, and then click OK. The tool now has your gas mole fraction information. If you notice, our estimated speed of sound is still the same. So if we want to get a current reading for the estimated sonic velocity of this particular gas composition, we just need to choose a different gas and then come back to the AGA8 gases so it can recompute it. So if you notice, if we go back to natural gas and then we go back to use AGA8 gases, you'll notice now that our estimated sonic velocity is 1318.89. If we now hit calculate, we will get our new application information. And if you notice, our spacing has changed slightly. Before it was nominal 26, now it's nominal 25. And that has to do with the speed of sound. So you could see how each little variable in your application has some impact on the overall configuration and installation of your flow meter. Again, if we choose, we can say, well, we don't want reflect for traverse, we just simply want reflect. And you can see, again, we've changed now our velocity limits and we've changed our spacing to nominal 18. And some of these values have changed because of the pressure that we've changed. So if we were to put the pressure back down to the original values of 400 and 800, notice our speed of sound changed again to 1336 now. So it's all very dynamic. Everything affects other things. Lastly, should you want a hard copy of the application that you've just created, you can come down to the bottom and click the print button. This will open up a dialog box that will allow you to name the file and also save it on your PC and choose the location to save it. The FS200 tool will print to the default printer, which is pre-configured in the tool itself. If you want to check to see what printer that is or change the printer, what you should do is cancel out of the print command and exit the tool, the utility tool. Come up to the File drop-down and click on Print Setup. And that will identify what printer the tool is recognizing and give you the opportunity to change it, to select a different printer. The FS200 Utility will always print to this pre-selected printer. It does not give you the option to select the printer at the time of printing. So you have to make sure you do it ahead of time. And once you've selected your printer, just say OK. Come back to the Utilities tab and the Gas tool, and then hit the Calculate button, and all your information will come back since everything is still there from before. And now you can just go ahead and print. So that's a bit of an in-depth look at the gas sensor sizing tool in the FS200 Utility. As you can see, the tool is very versatile to give you information about your application and to also show you what different selections will do in terms of the configuration of your flow meter. It'll tell you the recommendations, it'll tell you warnings in case you exceed a limit of operation of the flow meter, and allow you to ensure that your selections and your sizing of your flow sensors are optimal for your particular application. Thanks for taking the time to watch, and be sure to check out all the other videos that are contained within this grouping on the FS200 tool. Bye for now.
Siemens, ingenuity for life.